So I looked it up. I figured out what the problem probably was. One of the LEDs went out in the back. I'm going to try to fix it, but I might not even have time. And it may not even be worth it. So I just went and bought a new TV. So now I have a new TV, but it's not like a good story new TV. It's because my old TV died. So that was my news for the weekend. I don't know. Today, we're going to talk about seismic waves. I almost said science waves. Seismic waves. These are what the earthquake is basically made of. Why does the earthquake travel through the earth? Why does it shake things? How do we even know that all that pressure has been released? It's the release of seismic waves. And they're actually pretty complicated. Seismic waves do a lot of different things. We use seismic waves that we create to explore underground. Because we can't dig everywhere. We can't drill a hole everywhere. Close your Chromebook. Close your Chromebook. So we can't dig everywhere. We can't drill everywhere. And drilling is expensive and digging is expensive. To dig like a mine or a pit or an oil well is bare minimum going to cost millions of dollars. The rigs that they rent, all the trucks that have to be there, all the personnel, and you have to pay the landowners. Drilling a single oil well is well over $1 million right now. In fact, in a second, I might look up the cost for that. But if you drill even just one well that's dry, your company has taken a major hit. And so before you start to drill oil wells or look for new coal or metals or whatever you're trying to explore for, you want to throw some seismic waves down there and see if you can get a map of the underground and try to figure out what's going on so you know where to drill and you know you're going to make some money, or at least you improve your chances. So the seismic waves are what help us do that. First off, we kind of discovered seismic waves just by understanding the earthquakes. So we didn't know about these first. The earthquakes taught us about the seismic waves, and we kind of went from there. So they talk about the 2010 Haiti earthquake. We actually went over this in detail in my dual credit class, but this is a relatively recent, devastating earthquake that happened in Haiti. If you're not familiar with your geography, Haiti is down in the Gulf of Mexico, actually attached to the Dominican Republic. Very interesting dynamic there. But this was a very large earthquake. The infrastructure for the city was not very good. They had a lot of crumbling buildings, a lot of destroyed infrastructure. It cost a lot of money. The United States sent a lot of relief over there to help them out. And basically, it was something that the scientific community probably had a good idea that it was coming, but the country itself just didn't have the resources or the planning to like earthquake-proof all of their stuff. And that's where it comes in. It just like you can kind of relate this back to the Texas snowstorm disaster. It may be uncommon, but you can bet that it's going to happen at some point in time. And how much are you willing to pay to make sure that it's not very bad for you? In Texas, we were willing to pay nothing. And so as soon as it started to snow, all of our electricity stuff shut down. We were not winterized at all. And it cost people days and days of their lives. It cost some people their lives because they didn't have any heat. In Haiti, they probably knew the earthquake was coming. They didn't set up the infrastructure that they had. And there's various reasons. Economy, ability to govern how people build buildings and what to do with old buildings. This is all very touchy, but we deal with this all the time. California deals with it a lot. Japan is kind of like the best example of how to retrofit buildings and plan your country to be able to shake and not fall down. It's the kind of the old saying, bend but don't break. If your buildings can sway back and forth, they can survive an earthquake. If they're very rigid and they start to shake and they just break and fall over, that's not going to be a good deal. You want to have your city set up where, if an earthquake strikes, it's not going to be ultra devastating. So they go through a couple example earthquakes here. Maybe in a little while, this is only a minute. Let's watch this. So this was a California earthquake, and I think this is going to be the one where the highways collapse. It looks pretty old. You can see the shaking. This is in a classroom. Imagine if this happened in our class right now. They're in the gym. Hold on a second. Let me get the speaker going so we've got some volume y'all can listen to. Shush. Come on. There we go. Come on. Okay, well, maybe the speaker's not going to work. I'm bad. I thought they would, but. Car alarm's going to look at the window shaking. And this was one of the bad parts. Actually, let me go back just a second. They might show it in a second here. California has these double-decker highways. Has anybody driven through Austin and seen the double-decker highway? Yeah. 35, they don't have room to build it wide like we like to here in Texas, so they built it tall. They got a lower 35 and an upper 35, and it goes the same way. Just one road is on top of the other, like a bridge on top of a bridge. They have lots of those in California, and during this earthquake, the top level collapsed down onto the bottom level. And so literally this is like a sandwich, and there's like hundreds of cars trapped in here. This was a really bad, devastating earthquake for the area. I think we're talking early 80s, maybe 1980 exactly. I don't remember the exact date. They might say it in a second. Just say 89, so late 80s. I was on the opposite end of the decade. But yeah, lots of devastation here. One of the things they showed a fire, we bury all of our important stuff underground. Gas lines, electrical lines. And so when the earth shakes and cracks, it cracks our gas lines, cracks our electrical lines, and causes a lot of devastation. That was one of the cars that got all crunched up when the highway collapsed. Big fires. You can see, look at this whole section of road that's just collapsed. You can see this one's actually still standing, and you see how far the section next to it collapsed. And so even if you were on the top section, you probably drove off like a good 5-6 foot cliff when you got to one of these other sections. And you're not leaving off of here. You literally have to wait for a fire department to come with a ladder and get you off of the top part of the highway. There's no way for you to drive down. And so this was a very crazy earthquake and a very packed part of the country. And that's it. We don't need to go through all this. We're not really focusing today on the earthquake itself or the damage it's caused. We're focusing on the seismic waves. And let's see what they go through here. Basically, the seismic waves are essentially like sound waves. And we talked about this a lot. When we build up that strain and pressure and something eventually snaps and it releases and all that energy is released, you have like a sound wave that travels through essentially. In the air, sorry if this is too loud, but when you hit something, when you have that pressure release, it's going to vibrate the molecules right here where the stick hits the table. And that's going to travel across the room, hitting all sorts of air molecules until eventually that pressure wave comes through and gets into your ears. Your ears feel that different pressure, and they interpret it as a sound. That same pressure wave can travel through the ground. If something big gets dropped on the ground, like let's say in the weight room, do you ever feel like when somebody's squatting a lot of weights and they drop the bar, you ever feel it hit the ground? I don't know if y'all do or not. But if you do, that's the same kind of seismic waves. You're releasing energy, that kinetic energy as it hits the ground is transferring into the ground. It's not going to hurt you. It's not like a lot of energy, but it does travel through the ground, hit your feet, and kind of go up your feet, and you can feel that shock in a way. That's the same thing that's happening with these seismic waves. Now, as we studied seismic waves, we saw that there are several different types. There are different things that are happening inside the ground. So the first one they have is P wave. The P wave is the first wave to come. It's the fastest wave. And this is actually not the one you really need to worry about. These are the ones that kind of warn us that an earthquake has happened. P wave is the fastest, which means if it's the fastest in a race, is it going to come in first or last? It's going to come in first. So it's the fastest one. It's the first one to arrive at the finish line. And the reason is it travels in a forward and backward motion. So as it's going, it's kind of, let me see, as it's moving towards the door, it's shaking like this in a forward and backwards motion, and it's able to travel very fast because of that. So those are your P waves. Think of P. This is not what P stands for, but it helps you remember it. Think of P as primary. Primary means first. P wave is your first wave to arrive. It's the fastest wave. Next, you get your S waves. S waves arrive a little bit slower. They're not the slowest wave, but they're not the fastest. S waves are, you can consider them secondary waves. That's what they kind of call them. That's not what the S stands for. And these travel, they're not the fastest. I'd say they're like the middle waves. They're not the first, they're not the last. Let's say middle. And they're going to travel in a way, I guess that's hard to draw on the board. If S waves are heading towards the door, like the earthquake happened over there, and I'm standing over there, I'm about to feel the earthquake, the S waves travel like this, left and right as they move forward. So imagine, I don't have one here. I guess I could have like a cable or something. Let me grab this. This will work. Yeah, that'll work. Why not? So for those of y'all that can see, imagine like this is on the ground and you're swinging it back and forth. That's not going to work. Anyways, I thought it was going to be a good demonstration, but it wasn't. They're traveling like left and right as they move forward. So it's almost like a left and right shake that's spreading out in all directions. These are called shear waves or secondary waves. They arrive second and they move in a different way than the P waves do. Yeah.
Zigzag like this, or is it like a snake?
Almost like an S kind of snake.
So is it like elongated, or is it just like back and forth?
So look, you know when you do the rope, the arm rope thing, and it's like attached at one end, and you're doing the S like that. It's like that, but sideways. Yeah, where you're doing it like this, and you see the S. The rope is going back and forth, but the S is traveling away from you. That's what S waves are kind of doing. And they might have a picture in a second that shows it a little bit better. They're going to arrive a little bit slower. And the key here about the S waves, these are really important to science because S waves don't travel through liquids. And so one of the things that some people ask when we talk about the earth, and we talk about the core and the mantle, and we say that like the outer core is liquid, but the inner core is solid, and the mantle is kind of solid. We know that because of earthquakes and because the way that S waves travel through the surface. They cannot travel through liquids. And so we know wherever we see S waves, we know that substance is a solid. As soon as you get into liquids, the S waves just die. They don't go any further. And so anything that has S waves in it has to be a solid. Now, we get to surface waves. Surface waves are the slowest waves. Surface waves are also the ones that cause the damage. If you're in your house and you feel an earthquake, you're not feeling the P waves or the S waves. Those are too subtle. We can pick them up with instruments, with seismometers and earthquake detectors, but you're not going to be able to feel them in most cases as a human being. They're just barely there. The surface waves are the ones that we feel. They're the ones that do the damage. They're the ones that cause all the problems. And rightfully so, because where do humans live on the earth? In the surface. If we all lived like underground like moles, maybe this would be different. But we live at the surface. We build all of our stuff on the surface. And so the surface waves that travel along there are the ones that are going to affect us. So when you see the roads all messed up, when you see buildings fall over, those are the surface waves that happen. And there's actually a lot of these. Some of them kind of move like waves in circles. There's lots of different ways that surface waves can move, and I don't know that they're really going to get into those because it's a little bit beyond this class. But those are your three different types of waves. P waves are the first to arrive. They're the fastest. S waves show up just a little bit afterwards. They're like in the middle. And then their surface waves are the slowest. They will get there last if they get there at all. If we're really far away, like we're here in Texas, and an earthquake happens in California, I will read the P waves and the S waves on my seismometer. I will not get any surface waves. They just won't travel that far. They kind of lose their energy as they go along. So let's see. Let's see what this guy's got to say about surface waves.
Part 3, the Earth's interior plate tectonics. Section A.
Let me see if I can get this speaker.
The Earth's interior.
When the Earth comes loose with some big release of energy, like movement along the wall, it can cause an earthquake.
Yeah, I mean, I'm going to watch this video. Sorry, everybody.
The elastic rebound theory.
Oh, that was weird.
When rocks get stressed enough, they're likely to
Could have just used like a rubber band or something.
The stress pulls and pulls, and the rocks get all they can until they rupture. The energy released from the rupture moves outward in waves from the rupture site. The point within the Earth where the fault ruptures
Types and sizes go along the surface.
Yeah, that'll help a little bit.
Body waves and surface waves. Body waves travel through the Earth in an accordion-like push-pull sort of oscillation. Surface waves ripple along the surface of the Earth
Well, I
and
can't
are
get the
similar
speaker
to the
work.
rolling motion of ocean waves.
Seismographs record the
Also called
waves are not only slower than P waves, but they
Okay,
can
no,
only
this is not good. We're not going to watch this. Sorry. Okay, so focus and epicenter. They'll no doubt ask you about a couple of these. Know that the focus is where the earthquake actually happens. It's underground. It's where the slippage happens and your energy is released. The epicenter is where we put it on the map because our maps don't have the underground. And really, we don't care about how deep it was. What we care about is what street is the center of the earthquake on, where's it going to be messed up at, and how far away are we going to have damage. Was my house damaged or was it not damaged? I need to know where the earthquake was at. So the epicenter, the one we talk about more often in the news when you hear about earthquakes, that is on the map at the surface. The focus is where the earthquake actually occurred underneath this surface, and all the energy was released. So this is only 17 seconds. We'll watch it.
Focus is the point on the wall where the earthquake originates. The focus is also known as the hypocenter. The epicenter is the point on the surface directly above the focus.
There we go. Okay, and let me go ahead and turn this on now. There we go. Let's see. Measuring seismic waves. You have a seismogram. Using seismometers. Okay, so they're getting into this. Real quick, let me grab this. Here's how our earthquake detecting machines work as we discover an earthquake in progress. I actually bought one of these. It works all right. We got a lot of interference around here, and it's not the greatest one. But here's what you have. You have a magnet. You got a roll of wire, and the magnet kind of has to be suspended above it. And you can kind of see that it will move. It's not super well set up right now. But if I tap it, it's going to go up and down just a little bit. It kind of floats above everything. So what happens when the earthquake happens? It's going to shake the ground. It's going to shake the bottom part of the seismometer, but the magnet's allowed to move or kind of stay in the same place. So the magnet moves relative to the little spool of wire. If you've taken physics, you know that's going to create some electricity. We pass the electricity into a computer, and the computer reads how big our earthquake is, how much shaking is happening. Now, at that point, we have a problem. I don't know, with that machine or with any machine that we have, I don't know what direction the earthquake happened in. What I can do, based on when the waves arrive, because I know the P wave is going to arrive the fastest, I know the S wave is going to arrive in the middle, and the surface wave is going to arrive at the end. Based on how far these are apart, I can figure out how far the earthquake happened away from me, but not what direction. So what we have here is we got to do a little bit of math to figure out where the earthquakes are. If I have, this is going to be terrible. I'm going to apologize in advance, and y'all can forgive me.
Gosh, this is so hard to draw.
Yeah, it's tough. Yeah. So there's Texas. We have our seismograph here in DFW, and I receive an earthquake. And I do my math. I look at the waves, and I find out that my earthquake was 300 miles from here. Again, I don't know how big Texas is, or how far 300 miles goes. I assume it's going to be somewhere in the state. Maybe not. So 300 miles away. Let's just forget about scale and everything. I don't know what direction the earthquake happened in. All I know is from right here where I'm standing, it was 300 miles away. So what I do is I measure out 300 miles on the map, and I say that's 300 miles. It's probably a lot shorter than that, but 300 miles on the map, and I can go in any direction. So 300 miles in all directions will essentially get me a circle. And I don't know where the earthquake happened on that circle, but I know it happened somewhere on that circle. Now, to figure out exactly where the earthquake happened, what I need, as you can see in this picture, is actually 3 seismographs. If I have 3 seismographs, I can figure out where the location is. This is called triangulation. Triangulation is used in all sorts of stuff. If you're into like marksmanship shooting, triangulation is what you need to do if you want to shoot long distances. You can't see that far what direction you really need to be aiming. So you get someone, a spotter, off to your side, and now as y'all are looking, you form a little triangle. You know how far away from you your spotter is. He tells you what he sees your target as being, and you see it as well, and it forms a little triangle, and you can figure out exactly where you need to be. This is the same thing, but instead of triangles, we're talking about circles, but it's still triangulation. So watch what happens if I add a second location. Let's say up here in Amarillo, I have another earthquake detector, a seismograph, and it picks up the same earthquake, but it says it's 500 miles away. So I measure out 500 miles in whatever direction, let's say it's over here, 500 miles, and I make my circle. I know my earthquake has to be somewhere along this circle that's 500 miles away from my thing. It's not the greatest circle, but there it is. Now, if it has to be on this circle and it has to be on that circle, now I have my earthquake narrowed down to only 2 spots. It's either going to be right here or right there where those 2 circles meet. So now with a second location, instead of just saying, I don't know where it happened, it was somewhere 300 miles away from here, now I have it narrowed down to these 2 spots. And if I add in a third location, let's say down here in Galveston, and that's 800 miles, because why not? If I add a third location and everybody does their work right, they all do their math right, all 3 circles should meet only in one spot. And that one spot where all 3 circles meet has to be where the earthquake happened. And so it takes a little while to do this work. Somebody has to have information from all 3 places, but that's how we triangulate the location of earthquakes. And that's kind of what they're showing you here. One circle alone won't get it. 2 circles narrows it down to 2 places, but that third circle confirms exactly where the earthquake happened. I know it happened right here and not anywhere else. Let's see what else we got. So this is a little chart. I don't think we're going to use this chart or teach it. This is actually a pretty complicated chart to use. and I spend like a full day going over it in my dual credit class. So we're not going to spend any time looking at that chart. But we can keep going. To the next page. Quantifying the severity of earthquake. So how bad was the earthquake? How much did it shake? The main one we use is the Richter scale. The Richter scale is the one we're used to. 5.0, 6.0, 7.0, those kind of earthquakes. That's the Richter scale that they're talking about. And what that does, that is a rough estimate of how much energy there was and how much shaking there was. There's a newer one called the moment magnitude scale. The moment magnitude scale is actually based on the amount of energy released, and it has to do with how much shaking happened at certain locations. So each number on a lot of different scales, actually power of 10, yada, yada, yada. Let's see. I forget what they're trying to describe there. Let's keep going. The numbers on the Richter scale, logarithmic. Yes, so this is something important that they're going to ask you about. For the Richter scale, for every one step up on the Richter scale, so like a 7.0 earthquake versus an 8.0 earthquake, it's going to release 32 times more energy. So an 8.0 is 32 times worse for shaking and energy release than a 7.0. And so they get really bad. That's why a 3, not that bad. You just have a little shaking, like your pictures just rattle on the wall. No cracks, no problems with your house, you're good. A 9, like your house probably isn't standing anymore, unless it was specially built to withstand earthquakes. They're very, very strong. So remember that 32 times. For every one step up on the Richter scale, 32 times more energy is released. Your earthquake is 32 times worse. Then they give you a little bit of math just to show you earthquake intensity. Oh, so now the next one, we have modified Mercalli intensity scale. And this basically goes from 1 to 12, and it's based on how much shaking there is for humans. So notice the bad one. 1 is instrumental, detected only by seismographs. People don't feel it. There's no damage. It's just a tiny little earthquake that only the computers pick up and no humans even know about unless they're looking at the computers. Versus number 12, listen to the things they describe here. Total destruction, literally trees are falling down because of the earthquake. The ground rises and falls in waves. So remember what I was talking about earlier with the ropes, where you do the ropes in athletics and you're working your arms and it gives that big curve. Imagine the ground doing that coming towards you. Those are the really bad earthquakes. You can literally see waves in the ground like waves in the ocean. And so this is a detection on what people are experiencing within an earthquake and how bad that is. So you have everywhere from not too bad at all, we wouldn't even know it happened if you didn't tell us, to literally the ground was like water waving up and down. Cars are getting thrown into the air. Buildings are definitely falling down. And this is going to be one of the worst earthquakes you've experienced. Let's see. I wonder if anybody's ever gotten that like on video, the actual ground moving. Be an interesting video if they had. Using seismic waves to study Earth's interior. Like I said, we use the different waves, specifically the fact that S waves don't travel through liquids to kind of figure out what's happening inside the Earth. Where we can't dig down that far, we can't drill holes that far. The waves can go everywhere. And so we use earthquakes as an advantage to read those waves. We trace them back all the way through the Earth. We can look at lots of different layers, lots of different things that are happening inside the Earth. And so one of the questions is, like, how do we even know this stuff? How do we know what's going on in the Earth? There's 2 cores and there's a mantle. It's earthquakes. Earthquakes send waves down there. We read those waves and we kind of build the inside of the Earth based on what we're getting from the waves. And the shadow zones are one of the things about that. Like I said, S waves don't travel through liquids. So where we see a lack of S waves, which is what they call a shadow zone, the S waves don't come through. We know that that's associated with a liquid. Something has melted all the way down. It's no longer in the solid phase. It's now in the liquid phase. So I think that's about it. Before I move on, real quick, this right here is another example of the electronic one that I had. In the electronic one, the base shakes, but the magnet stays the same and it produces electricity. Here, this is more a manual one. The paper's wrapped around this like barrel in a way. And when the earthquake happens, the barrel shakes, but the pencil stays still. And so if you see shaking on the paper, it's because the barrel's actually shaking. You have an earthquake happening. And the pencil is just sitting nice and still, nice and flat. And so these are pretty interesting. If y'all want, I can set up the earthquake machine and we can attempt to make an earthquake. I don't know if that would be something that y'all want to do or not. But if you want and you think it would be fun, let me know. And I will set it up this week and get it going. How much time we have left in class? 8 minutes. So I will not open it up an assignment today. We will start the assignments on this section tomorrow, either with the constructive response or the multiple choice. Maybe we'll do both. We'll see. So I want to get some assignments in and give y'all a chance to do the grade back up. So remember the grades. Remember missing assignments. If you go in and finish an assignment, send me an email, let me know, and I will update the grade book, and we will all be just a little bit happier. Okay. I don't think anybody's at home today. I need to do roll. I forgot to do roll Friday too. And y'all were gone. I'm like, I don't know who was here. I don't know who was not here. And apparently I'm